ended up just ripping it apart. So I want to make sure that you guys understand this so that when you go to work on your lab, you don't have any issues. So when we talk in terms of solids and liquids, okay, they both are matter. They both have volume. Okay, we can actually get volume with them. I mean, you can get volume of gas too, but the volume of the gas is going to take up whatever size of the container it is. Okay. They both consist of particles. Your solids tend to be highly ordered, whereas your liquids are not. These solids are locked into that matrix because the IMFs are very strong. Okay. They're at their strongest when the matter is in solid form. There are two types of these. There's amorphous and crystalline. So amorphous and crystalline are the two types. And then we have disordered particles where they're going to move around so that they can slide past each other. That's in a liquid form. They take the shape of their container. As far as shape is concerned, it's variable, but it'll take the shape of, the bottom part of the container, wherever it's in. It shares the properties of all liquids, which are surface tension, viscosity, and volume of mixing. These curves then, the heating and cooling curves, tell you how they're going to transition from one form to another. So in a solid form, the water is going to be locked into a phase, and we end up having it locked into that position, whereas in the solid, or in the, let me see if I can get this to go here. Maybe not, maybe not. Control click. There we go. So in the solid form, it's in this matrix. Now, why is this vibrating?
Particles are always...
Right, the particles are always in vibration unless this number is down to see what's happening to those particles? They're slowing, they're slowing, they're slowing. Now we're at 0 Kelvin. Do you see how they stop moving? That's the whole idea of absolute zero, is that these are going to stop moving at 0 Kelvin. Now we're going to heat these up. We're getting hotter, we're getting hotter, we're getting hotter. That solid is warming, okay? It has some IMFs here. This is neon gas, okay? So now some of it's forming. It's in a liquid form because it's sliding past one another. Let me see if I can go to water here. That's going to make it a little bit easier to look at. Okay, water, we're going to go down to 13 Kelvin, maybe. So 13 Kelvin. That should be really, really cold.
It's 13 Celsius.
Oh, Celsius. Yes, you're right. Thank you. Why is it not going into a solid form? Maybe it is in the solid form for the water. See, here's argon. Okay, here we go. Here's argon. This is a solid. Okay, we heat it up. Now it's going to change, and it's going to transition into a liquid where the particles can slide past one another. Now, a couple of these are flying off and becoming vapor. Why? Oh, then it came back. That happens, okay? At the surface, you end up having evaporation occur, even in a liquid. And that's why if you leave a cup of water out, for days and days and days, eventually it's going to go away, okay? If the thing's capped, the volume will stay the same. But if it's not, then it's going to go up in the air, okay? So heat this, it's going to go into the liquid phase, and then eventually it's going to go into the gas phase. And all of these particles are going to spread out and try to get as far away from one another as they possibly can. And they move around and they bounce off of the sides. And that's what causes the gas pressure in the container. Now, what is happening in terms of IMFs here? Are there IMFs present? It's in the gas phase. Nope. And by the time it gets into the gas phase, the particles are so spread apart that they're not going to hook together. Yeah, well, so in any gas that we talk about in here, all right? Now, in true gases, in the real world, okay, this is like in physics, they always do problems in a vacuum because life is just so much easier, okay? We like to talk in terms of ideal gas. So ideal gas means that there's no IMFs present, okay? Now, in reality, yeah, there's probably a few, and they're going to hook up, but they're not going to stay there long because those LDFs are fleeting. They're just in and out, okay? When we cool this back down, then, what's happening to our IMFs? They're getting stronger, and eventually we get into a liquid phase when we have those LDFs coming together, okay? And enough of them have come together that we've got that reestablished. But the particles are still able to slide past each other here. If we continue to cool this down, then we go into the solid phase. And what happens in the solid phase? They're really strong, okay? So gas phase, in theory, they don't exist, okay? We've gotten rid of them. In the liquid phase, they've gotten stronger. And in the solid phase, they're really strong. Does that make sense? Now, what has happened in terms of like boiling and cooling and all of that stuff? We're going to get into that today. But it's these IMFs that establish whether we have a solid, a liquid, or a gas phase. Okay, here's your solid, here's your liquid. They're sliding past one another. And here's your gas, where they're all spread out. That makes sense? Solid water, okay? We've got our hydrogen bonding, okay? They're trying to show you here with the water that water is less dense in the solid form than it is in the liquid form, and that's why ice floats. And then in the gas form, everything's spread out again, okay? And this solid phase, these cavities here, what are they caused by? Hydrogen bonding, right? Remember that? Okay. Because the way that this ice forms, and we'll get into that more today in this PowerPoint that I have. All right. So let's look back at this. Okay. So in solids, they have a specific matrix that's formed. Okay. And when we have a specific matrix that's formed, that gives us our solid. And it's the connections here between those IMFs, those forces that cause that to happen. Now we can have something called an amorphous solid where we don't have a regular repeating pattern. These cavities are different from one place to another. Do you see that? Rubber, plastic, asphalt, glass, wax, looks like Play-Doh's on there. So lots of stuff like that. Let me see if that'll show up there. So Play-Doh, all of those things have this. And if you think about a lot of these, you can kind of stretch those things. You can move them. They kind of flow over time. Does that make sense? And you're like, but glass? Well, have you ever seen glass in a really old building? Okay. It kind of pools down here at the bottom because over time, gravity is going to cause that glass to kind of move and change shape. All right. Now, that's what the amorphous solid looked like. This is what the crystalline solid looks like. Do you see the difference between this and this? This is what water would look like because it's not amorphous. Okay. You also have other places where you have repeating patterns like diamonds, graphite, stuff like that. All right. Liquids then show translation. What that means is that they're not locked into position, so they're able to move, and they end up taking the shape of their container. They cause different properties of different liquids due to those IMFs. So if we're looking in terms of one of the properties is viscosity. So do you remember the glycerin that you had? That was hard to pour, wasn't it? Because it was very viscous in that lab. Maple syrup is viscous. Oil. So this guy started an experiment back in 1930, okay? And he had this tar in here, and he put it in a funnel, and he's waited for these drops to fall. And at the time of this picture, it was 81 years. They've actually updated that. They've got it going further, but I'll pull up the data on that and we'll talk about that. So tar pitch experiment. There it is. Okay. I think there's like a Wikipedia. Yep, here we go. Good old Wikipedia. I know your English teachers don't like it, but sometimes it comes in handy. So this is that guy. Here's his experiment. Here is the results. So since 1927, okay, we're almost 100 years later, that 9 drops have fallen. Yeah. So here it took 98 months, 99 months, 86, 97, 99. Why do you think the months have gotten longer here? Any theories there? Yeah. Well, I would say that the tar was probably, I mean, at room temperature up here. Any other ideas? But that's a part of it. Yeah.
Just because there's less tar, so it takes longer.
That could be part of it. There's less pushing down on it. The other thing that I thought about was this was 1988. This is 2000. My guess is they probably installed air conditioning in that building. So during the summer, the thing didn't move quite as much as it had. You know, the climate was pretty much sustained and the same all year long. Versus here, if they had hot summers, England, most places don't have. This was done in England, Dublin, and Ireland. A lot of places over there don't have air conditioning. Like we stayed in hotels in England, there was no air conditioning in the middle of summer. It was hot. You know, it was like 80 something outside, and you're on the 4th floor and it's hot. But they only need it for like a month out of the year, so they just don't even bother. So it's expensive. But that would be part of my guess. So between, which is part of what you were saying, you know, it hardened, you know, it's going to be a little bit harder if the temperature is the same. So, and then the weight of the stuff pushing down on it. But this is quite a bit difference in months, going from 111 to 148 like that. You know, that's why I thought there's probably some other climate kind of issue. And then this kind of stabilized almost a little bit here. So between those two things, that's why I was thinking there's probably something else to it as in terms of climate. But I found that kind of interesting that, you know, that they're still keeping up with it. So anyway, yep, that's viscosity. The higher the IMFs are, the higher the viscosity is. Does that make sense? Because they're going to hold together with the other particles that are there and not get moved as easily. Okay? So high viscosity is going to flow slowly like that pitch. That means that they're going to have high IMFs. Surface tension is also another one. So we talked about this. You guys did a lab on that. That's why you can get like water to come right over the edge of the cup. You can get spiders or paper clips to be able to float on the water. Okay? And that's based on intermolecular forces at the surface. These molecules are linked together. And the stronger the IMFs, the stronger the surface tension. And that also relates to boiling. Okay? As they're reducing those IMFs, they've got to break through, that gas has to break through the surface So the stronger the surface tension, the stronger the IMFs, the harder it is for something to boil. So those molecules are attracted to each other. It's like a layer of that chemical attraction over the surface of the liquid, but we can reduce it. Do you remember putting the detergent, the soap in there, and that just went bloop? Okay, that's what detergents do. That's one of the things that they do, is they change the intermolecular forces, so it's easier to wash your hands and to do the different things that you need to do so that things mix together and move things off. Oh yeah, I can do that. Yeah, so this is a little video here. Do you think it's going to call it up? There we go. Yep, it did. Okay, so we don't need to have the audio on this because it's really annoying. So what they're doing here in this video, and it's a Bill Nye video, is they are going to mix. They're going to take 2 bottles here, and they're going to fill them. They're filling one with water, and they're filling one with alcohol. Is that what she's doing? Oh God, no, please no, please no. Okay, so here she's mixing, just telling him to pour some stuff. She's getting irritated with him. Okay. So she's going to add a cup of water in. Yep, she's making pasta. No, she's not going to boil it. So she's putting a cup in here. Okay. And then she's going to put a cup of alcohol. She's putting food coloring in it to keep the water, be able to see the difference between the two. And now she's going to put a cup of alcohol in there. Now this was the line when there was 2 cups of water in. So when I'm trying to get this to stop where I want it, there we go. So when they had 2 cups of water, it went up to here. When they do 2 cups of, or 1 cup of water, 1 cup of alcohol, it doesn't go up to that line. And that's because there's space in between those molecules that alcohol is filling. And that's why the volume's different. And that's going to come into play when we get into chapter 14, where we talk about solutions and why you need to use a volumetric flask versus just going with a graduated cylinder or something like that. So we're going to come back to this video and talk about this when we get into the section on solutions and why we use a volumetric flask when we are creating solutions, which is a lesson that my AP Chem kids need to learn because they had a question on their last test and it didn't go the way I wanted it to. All right, so this is your heating curve. This is what we were hoping for out of your lab yesterday. Okay, so this would be your solid. This is your ice. This is melting. And a lot of times with the melting in that lab, it doesn't get to be a perfect straight line here. Okay, so I wasn't expecting necessarily that. But I want you to notice on this graph, this would be like a perfect heating curve. What do you see is happening to my temperature here? Yeah, it stays the same. During a phase change, the temperature stays the same. Why? We're adding heat in. You had it on the hot plate. What's happening to those molecules in here? What is the difference between a solid and a liquid? What are we studying in this chapter? IMFs. So what is happening during that phase change? Yes, exactly. All of that thermal energy is going in to weaken those IMFs. That's what's happening. Okay? Once those IMFs are weakened and it's no longer, you don't have any solid present, then that thermal energy can go in to heating up that, what phase are we in here? Liquid. Then we get to this point, and this should have been a perfect straight line for 5 minutes on your graph. Okay? What is happening here to our molecules? What is the theme of the chapter? IMFs are going away, and that's causing the molecules to move farther apart. Good? That makes sense? Once all the IMFs are gone, we're in what phase here for everything? Gas. And at this point, then that thermal energy can go into increasing the temperature. Okay, does that make sense? So here, what's happening, if we flip this and do kind of a mirror image of this, and I don't know if I can do that on here or not. I think it'll let me do that. Format picture. I don't think it'll let me do it. Okay. Oh, maybe it will. No, that's just blurring it. I don't want that. There we go. Okay, figured it out. So this would be a perfect what? Cooling curve, right. Okay, so here we've got our gas. Here, what is happening? In terms of the molecules, what's happening? Right, we're reestablishing those IMFs, okay, that were gone in the gas phase. So we're reestablishing them. Those molecules are getting closer together. And what is this process known as? Condensation. So we're condensing these. This is the dew on the grass out in the morning. Okay. Here, we're cooling. And at this point, what are we doing to the molecules? We're freezing. And what's happening in terms of the molecules? They're getting closer together. They're reestablishing, or not reestablishing, but they're strengthening the IMFs. And then here we're cooling again. So here we're in the solid phase. This is the frost on your windshield. Okay. Can't believe I found that. That's kind of cool. Okay, so the temperature stayed the same because what's happening, they're dealing with those IMFs. In this case, they're reestablishing and then strengthening them. Added energy during the transition then is going to go into changing that phase. All right, so intermolecular forces can explain boiling point and melting point. The boiling point and melting point are determined by the substance's IMFs. The weaker the IMFs, the lower the boiling point and the lower the melting point. Those are the determining factors in those points. Surface tension. Higher surface tension is caused by higher IMFs. Capillary action. So capillary action is like a liquid moving through, like a paper towel when you lay it on the paper towel, okay? And certain liquids will move better or worse based on their IMFs. Vapor pressure. Yep, that's how trees work in biology. If you guys actually had, that's how the water moves up through the roots of the trees up to the top of the trees, is through that capillary action. Vapor pressure, okay? And this is where people get confused a little bit, okay? So One of the vials back there, when we were doing one of the labs, I walked by and one of the corks, as I was walking by, went and like came right out at me. It was kind of funny that it just happened while I was there. And that was caused by vapor pressure. That cork was not on there real oops, why will this not let me write on here? That's interesting. Oh, I bet I have to bring this one down. It probably won't let me write on the slideshow or on the presentation. So many ways to do things. Okay, here we go. Now I can draw. So that in that test tube, it was corked, but a lot of the liquid was changing into gas. And over time, that gas was increasing pressure to the point where with that cork not being on there real tight, it just popped it right off. Okay. So liquids, when you have a liquid that has low IMFs in a sealed container, the container's sealed, some of that liquid is going to be going into gas, and some of the gas will go back into the liquid, and it's kind of this back and forth motion. The lower the IMFs, the more of that liquid that's going to be up here. So this is high IMF. No, I'm sorry, low IMF. My bad. Bad, Libby. Sorry. Low IMFs will give you high vapor pressure, because more of that material will go into the gas form. Okay. High IMFs in a sealed container. So here's my sealed container. Here's my liquid. Very few of them are going to go up, and so you won't have as much pressure from that gas exchange between the gas and the liquid. Does that make sense? These are held tighter together, so fewer of them go up. So this is going to be high IMF equals low vapor pressure. So this would be like water. Water doesn't have very high vapor pressure. Gasoline, your hexane, your pentane, all of those, acetone, those things are going to have high vapor pressure. And they call that, they measure that in terms of volatility. I don't know if I spelled that right. Volatility. Yeah, I think I did. Okay, so that's volatility. So something with low IMFs tends to be volatile. Now, when you hear the word volatile, what do you think? Huh? Violence, like boom, like it's going to explode or catch on fire, right? A lot of liquids that are flammable, like gasoline and different things like that, a lot of things that are flammable are also volatile, okay? But one, they're correlated, but one doesn't cause the other. Does that make sense? So they tend to be, a lot of them tend to be, but the volatility doesn't cause the flammability. That's due to something else, which is higher up other classes that you'll get into in college. Okay. And then the last thing is misability. So do the things mix? Well, if they have similar intermolecular forces, then they tend to mix. So if things just have LDF and no polar bonds, anything that's just LDF, if it comes in contact with something with polar or dipole forces, they're not going to mix. And that's why your oil and water don't mix. Because these LDFs aren't going to be able to get in between these molecules that are polar. So you've got water molecules here. You've got another water molecule, and it's attached to another water molecule. And you get something else coming in there that's trying to break in and mix in with this water. It's not going to let it in, because there's too much of an attraction between these two molecules. That's something that's trying to come in here and get in between those and mix in. It's not going to let it in. It's a very exclusive club. And it's like, no, you're not getting in here. Forget it. Okay. Come on, there we go. So, like I said, intermolecular forces are between these molecules, and that was one of the things on the lab that somebody turned in. They had straight lines drawn. They had this drawn as a straight line, just like these. Why would I be sad about this? Why is it wrong? Oops. Yes, it should be weaker. The bonds between these atoms here are much stronger than the bonds between the molecules. The bonds between the molecules are much weaker than the bonds between the atoms. Remember, one of the things that I like to talk about is like my arm, right? Okay. Could you rip my arm off of my body? Yeah, it happens. Machinery, that sort of thing will pull somebody's arm straight off. Not likely, but it happens. Okay. Now, if we hold hands, how easy is it to pull us apart compared to pulling my arm off of my body? A lot easier, right? Okay. So this is like the IMFs. This is like the bonds between the atoms. Okay. It can happen, but it's not as likely. He's so weak. If intermolecular forces are weaker, they tend to spread apart. If we make them stronger, they're going to come together. Okay. These intermolecular forces then are the determining factor in whether you have a solid, liquid, or gas. It also, you know, when we cool things or heat things, that's what's going to change is the IMFs. That's what we're changing in those phase changes. Okay. The surface tension. When we talk about surface tension, mercury, we used to have mercury like back when I was in high school that we could actually put in our hands and kind of roll around and play with. They don't, you know, it probably cost me an IQ point along the way. I don't know, but it was fun. It's the vapor that comes off of them that's the problem. So when we talk about something in terms of high surface tension, these have very high intermolecular forces. So the molecule itself is going to be very attracted to the other molecules in that sample. Water then is kind of medium, and alcohol is less than that. This is also what causes your meniscus to form. So when you have a meniscus forming in your, well, we always tell you read from the bottom of the meniscus, okay? That is because those water molecules are actually getting attracted to the side of the container. So this is called adhesion when it's attracted to something else, and it's called cohesion when it's attracted to itself. So water compared to mercury, if you look at the meniscus on the mercury, its meniscus is actually like this because it has a greater cohesive force than it does an adhesive force to whatever thing it's placed in. Container. That's the word I was looking for. Container. Okay. So capillary action is that movement up a tube, or it could be through a porous substance. Water has a really good capillary action. Cohesion then is attracted to one another. Co means the same. And then adhesion is attracted to something else. Okay. Like I said, some substances like mercury are more attracted to themselves than they are to their surroundings. Vapor pressure then, we talked about that a few minutes ago. We talked about volatility. Phase changes, are you guys familiar with these phase changes, what they are? So sublimation, you go directly from a solid to a liquid. We talked about these back in chapter 3, I believe. And then gas, you go from a gas right to a solid. So this is like the frost that's on your windshield in the morning. It's going from humidity in the air right to that ice on your windshield. Okay, those are just the phase changes. Those are available for you. Phase change diagram then. This is what you went through yesterday with a phase change, but this phase change diagram actually has pressure and temperature here. And there's something right here that's called a triple point. This triple point is the point where a solid, liquid, and gas exist at the same time. And it's only at a certain pressure and temperature. So let's see if I can find, there's a video out here of some triple points. YouTube triple point water. This is kind of cool here. And I don't even think this video has sound on it. Yeah. So here they're starting at triple point. So they've got it in there. They've actually got this in a vacuum chamber so that they can get the pressure where it needs to be. And so you've got solid here, and then you can see every once in a while it's boiling, it's bubbling here at the surface. There's a little, see the bubbles? There's one. You're getting more bubbles forming now as they're getting the, yep, there's the water boiling. See it? So you've got solid, liquid, and gas all at the same time. So that's called a triple point, but it only happens at certain pressures. So that, like I said, they're going to get the pressure here down to 0.006 atmospheres and 0.1 degrees Celsius. So it's right at, you know, the normal freezing point, but then they've got to change the pressure to get to that. So you can do that with different substances. And that's it. So this presentation will be on online for you. I will have it uploaded. So if you need it to be able to finish your homework tonight or your labs, I'll also try to get, if you need to print it out, I'll try to put it up on a PDF of the printout of the